So Astrid defended her thesis in 2012. She had prepared it between IPAG, the Institute of Astrophysics and Planetology of Grenoble, and the Astrophysics department at the CEA Saclay. And then she was successively a postdoctoral fellow at the University of Wisconsin-Milwaukee and at Caltech. And in 2019, she got her current position as chargée de recherche at the CNRS at the Observatoire de la Côte d'Azur in Nice. So Astrid is initially an expert in hydrodynamic simulation of stellar ejection in a wide diversity of astrophysical contexts, but always related to massive stars and compact objects. So for example, she studied the interaction of a pulsar wind with the wind of a massive star in a binary system, the deceleration of a gamma ray burst relativistic ejecta, or more recently, she also worked to simulate in great details the wind of for instance, Wolf-Rayet stars for the interpretation in a binary system, always for the interpretation of high-resolution images like those produced by the SPHERE instrument at VLT. And so since her PhD, Astrid has extended her expertise in many directions. And currently, she's particularly interested in the study of the population of compact objects revealed by gravitational waves. And for instance, to study the constraints on stellar evolution in binary systems, which can be obtained with this new messenger. So I think this will be one of the topics of our seminar today. So Astrid, please, you can start. Thank you.
Thank you, Frédéric. Let me see if I can do this up. So now you can see my screen and you can see the slides.
Yes, it's perfect.
Okay. Well, good morning, everyone. Thank you for coming. So I'm Astrid Lamberts. I work in Nice. I actually split my time between the Laboratoire Lagrange, where I officially work in the stellar physics group, and the Laboratoire Artemis, which is a smaller lab where people are specialized in the design and the use of detectors for gravitational waves. And so with them, I'm a member of the Virgo and the LISA collaborations. So today I'm going to talk about gravitational wave progenitors near and far. And so I'm coming to gravitational waves with a, I guess, with the perspective of a stellar astrophysicist. And when people think about massive stars and massive binaries, people usually think about observations you can do with a ground-based telescope. Or if you're a little bolder, you can think about binaries where you have one compact object and you can think about X-ray or gamma ray emission. But I actually think that the key result in the past 5 years on massive stars was with the detection of the first gravitational wave event. The very first event came from the merger of two black holes of 30 solar masses, and nobody really had predicted that we would detect such an event from the beginning. And so I'm trying to understand what gravitational wave events can learn us about stellar evolution in general. In this talk, there will be astrophysics and gravitational waves together, obviously. So what are gravitational waves? Well, if you actually ask Wikipedia, very simply, a gravitational wave is a ripple in space-time, which means that if a gravitational wave comes between two objects, it changes the relative distance between the two objects. Now that change is actually really, really small. And it's essentially 20 orders of magnitude smaller than the initial separation. And because it is so small, obviously it's extremely hard to detect. And this is why it took essentially 100 years between Einstein's prediction of gravitational waves and the actual detection. So we're talking about really small changes in space-time. And so obviously we're searching for the most extreme changes possible. And so they obviously come from compact objects and explosions. very extreme phenomena in the universe. Now, gravitational waves only come from objects or systems that have a quadrupole moment or moments beyond. So if your object is perfectly spherically symmetric, it is not going to emit gravitational waves. And so this is why binaries, because if you have two stars and they do this, there is a quadrupole moment. This is why binaries are, in general, good sources of gravitational waves. So we're looking for binaries. We're looking for compact objects. So gravitational wave sources mostly come from binaries made of black holes, neutron stars, or even white dwarfs. So in this talk, it will be a lot about black holes, a little bit about white dwarfs. I don't really work on neutron stars, but they are also very good sources of gravitational waves. So there's many things we can learn from gravitational waves. There is obviously fundamental physics. The LIGO and Virgo detections are currently putting new limits on tests of general relativity in the strong field regime. You can also use it to test theories beyond general relativity. Now, if we think a bit more about astrophysics, for me, obviously, gravitational waves are, I mostly think about the evolution of massive stars and the formation of massive stars. People are also using gravitational waves to put new constraints on the equation of state of neutron stars, which have a density that is beyond anything that can be reached on Earth. So gravitational waves are a great way to study very dense material. Now, in one case, we've had a gravitational wave detection with an actual electromagnetic counterpart. And in that case, there are many more things we can do. It allowed a completely different measurement of the Hubble constant with very different biases from all the measurements we have. Now, since then, methods have been designed to actually measure the Hubble constant even without the electromagnetic counterpart. But if we have an electromagnetic counterpart, we can connect the gravitational wave emission to the kilonova or the gamma ray burst emission. We can obviously learn a lot about the accretion onto the newly formed compact object and the ejection of often extremely hot, extremely relativistic material. And then if you have an electromagnetic counterpart, we've seen with the kilonova from the first binary neutron star merger, that binary neutron star mergers are a site where the Earth process elements can be produced. And this is something we did not know for certain before the BNS merger detection. And if you have an electromagnetic counterpart, it also means that you will have an idea of the host galaxy of this merger. And so you can connect the gravitational wave event to global star formation and the dynamics of the galaxy in general. So there is a wide range of astrophysics and physics you can do with gravitational waves. I will be mostly focusing on massive stars and the connection to global star formation, but there are many things that actually connect to most domains of astrophysics. So this is actually the spectrum of gravitational waves that we expect. So here on the x-axis is the frequency of the gravitational waves. And if you have a binary in a circular orbit, the gravitational frequency is simply twice the orbital frequency. And on the y-axis is what we call the strain. You can think about it as the gravitational wave flux. The higher the strain, the louder your object. And so currently, the detectors we have are kilohertz detectors. So the LIGO and Virgo detectors that you can see on the right. And so kilohertz means that the objects are turning around each other 1,000 times per second. Can you imagine two objects turning around each other 1,000 times per second? This is why we're looking at objects that are about to merge. And obviously, this means that these objects must be small, very compact. And so this is what we detect with LIGO and Virgo. We detect the mergers of objects that are relatively small. Supermassive black holes, for example, they also merge, but they will merge at lower frequency, and they will merge typically at in the millihertz regime, so 10 to the minus 2, 10 to the minus 3 here, and they will be detectable by LISA in 20 years. And that even, so this is the class of objects that are merging. But if you have a binary, what happens is that it emits gravitational waves. Through gravitational wave emission, the binary gets closer and closer until the merger. But we can also detect the gravitational waves that are emitted as the binary is just getting closer and closer. So that emission is less strong, but it's detectable. And so, for example, LISA will be able to detect binaries that are not merging, but they're just being binaries for objects that are close enough because the emission is low. And for example, LISA will be able to detect the emission of white dwarfs in the Milky Way when they are just turning around each other. And at the very lowest frequency, so the nanohertz, the 10 to the minus 9 hertz, we can actually detect gravitational waves with pulsar timing. And so this comes from, this are the gravitational waves you expect from supermassive black holes when they just turn around each other. And so I will not talk about this, but you should know that these binaries exist. So these, basically at lower frequency, we have binaries that are just turning around each other, and we call this in spiral. And at higher frequency, we have mergers. Now, looking a little bit into more detail about, there's actually a very wide range of sources. And with the current detectors we have, so in the kilohertz regime, we have detected compact binaries. But if we are lucky, we could detect core collapse supernova. We expect to detect also pulsars. If they have a little bit of a bump on the neutron star, then that bump will create gravitational wave emission. And then at lower frequency with LISA, so I've mentioned the merger of supermassive black holes. I've mentioned galactic binaries like white dwarfs when they are just turning around each other. But LISA, for example, will also be able to detect what we call extreme mass ratio in spirals. So this is the case where you have a stellar black hole around a supermassive black hole. And so in that case, the stellar black hole is essentially a test mass. And it's a fantastic way to probe the very strong gravity around the supermassive black hole. And so that will be a very interesting LISA source for testing general relativity, for example. So there is a very wide range of sources, and I will be focusing on stellar binaries. And so most of the work I've been doing assumes that the black hole mergers we see come from two stars that were born next to each other and evolved together until they made a binary black hole merger. And so I'm going to explain you a little bit how that process works. So to begin, you need stellar astrophysics. You need two massive stars, let's say at least 30 times the mass of the sun. The problem with massive stars, one of the major uncertainties, is that massive stars lose mass. And because of these strong stellar winds, if you have a star that is 30 solar mass at the beginning, maybe it will only be 10 solar mass before it turns into a compact object. But that mass loss is very uncertain, and it is one of the main issues we have when we try to model populations of compact objects. We know that if your binary is close enough, there will be some type of mass transfer, especially when one of the stars becomes a giant. And then very shortly after, the primary star will explode in a core collapse supernova. Maybe there will be a long gamma ray burst. And the supernova is another problem we have, because the supernova explosion is asymmetric. And that means that there will be, the newly formed compact objects will have a kick. And so you have a binary, you explode on one side, and you have a big chance to break your binary. And if your binary is broken, you are never going to make a binary black hole merger. And so the impact of this kick, the magnitude of this kick, is something we don't really know, and it's one of the main uncertainties as well when we try to model gravitational wave progenitors. Okay, let's assume we have formed a binary with a compact object, And sorry, we'll talk about that later. One thing I wanted to mention here is the importance of metallicity. So metallicity is anything beyond helium. If you have a massive stars are very hot, which means that they make a lot of UV. And so those UV photons actually will interact with the outer layers of the star. And let's say you have a low metallicity star, then the outer layers are made of hydrogen and helium. And so the cross section for the radiation pressure of the photons to the atmosphere is pretty small. So there will be a little bit of a stellar wind, but not much. If you have a high metallicity star, then your atmosphere is filled with much more complex atoms. And it is much easier for the UV photons to basically interact with the atmosphere and push it away, and it creates a much stronger stellar wind. And so stars with high metallicity have very strong stellar winds, and that means that stars with high metallicity will only make very low mass black holes. At solar metallicity, if you form a star that has 100 solar mass, we're not even certain you can make a black hole with it because it's going to lose so much mass in the main sequence and through the several later stages. Low metallicity stars, on the other hand, you keep most of the mass in the star and you can form much more massive black holes. But we don't really know exactly how the mass evolution happens. But for example, for the first gravitational wave detection, this is just one model, but it predicts that the progenitor stars was at most 20% of solar metallicity. And that is actually a very strong constraint. So we've talked about stellar physics. Now let's see what happens when we have, on one hand, the secondary is still a star and the primary has turned into a neutron star or a black hole. You can do a lot of exciting high energy astrophysics. You usually have a phase of high mass X-ray binary. And then at some point, we know there must be a phase of common envelope. So the common envelope phase happens when one of the stars becomes a giant and the other star is completely in the envelope of the other star. And so there is a lot of friction, which brings the stars much closer together. And this is necessary because otherwise the binary will never merge. So on one hand, the binary gets closer together, and on the other hand, the envelope gets ejected from the system. So this is the theory. In reality, it's something we don't understand well. It's very hard to model. It's extremely hard to observe as well. So it's another uncertainty in the models we have. So let's assume we have had a common envelope, then the second star is going to explode as a supernova. And we now have two compact objects, and they will take billions of years to get closer and closer until they finally merge. So this is the story of how you make a binary black hole merger. Now, in reality, all of this, the beginning, takes less than 5 million years. So it's extremely fast, but complicated. And then the final stages take billions of years. Just as a reminder, the universe is about 14 billion years old. And so this means that you can use binary black hole mergers as a tracer of star formation a long time ago, because there is a long delay between the time you form the star and the time where your black hole merge. But the properties of the merger, the masses of the system, for example, they are completely set by binary evolution, which happens on short timescales. And so basically what I do is using gravitational wave detections to understand binary evolution and global star formation. So the problem with binary evolution, we don't understand it very well. So I've talked about the issues we have understanding the mass loss, understanding how masses can be transferred from one star to another, and the impact of supernovae in general. So because we don't understand this really well, binarity is something that people often ignore. For example, actually in really good stellar evolution codes, they're mostly all just about single stars. But 70% of the massive stars are in binaries. So those codes effectively cannot be directly applied to 70% of the stars. The fact that most massive stars are in binaries is also mostly ignored when people do galaxy evolution. But it actually does matter. It has impacts on the location of supernova explosion. There's impacts on reionization, for example. And for people who do large-scale surveys, binaries are often just a contamination. Oh, I have to worry about the binaries, they're complicated. But I like binaries because they have many more observational signatures than single stars. The only stellar black holes we have ever found are in binaries. And so it's in binaries that you can often measure masses, radii, and things like that much better than for single stars. And I like binaries because you can do very extreme astrophysics with them. You can accelerate fluids to very high energy, accelerate particles, do very interesting hydrodynamics, emit gravitational waves. And so most of what I do is study the emission and the dynamics of binaries through the different stages of their life. And so I've worked on individual systems and on the global population. So individual systems, that is something where you need a lot of observations and you try to do a very detailed model. So I will not talk about that today. And then for the global population, I try to understand it through gravitational waves. But I'm also thinking more and more about what we can learn with electromagnetic surveys or combining both. And so today I'm going to talk about how we can make better models for gravitational waves by using better models for star formation in general. So we're going to walk a little bit through this spectrum of gravitational wave emission. So first, we're going to talk about massive binary black holes. And by massive, I mean 30 solar mass. So black holes that come from stars, not supermassive black holes that come from galaxies. And then we will go a little bit deeper into the type of objects we could expect in a galaxy like the Milky Way. And then I will just open up in a little bit about what we expect in the future, which I think will be very loud and very bright. So where do massive binary black holes come from? So I guess you have seen this picture a few times now. This is our current understanding of the neutron stars and black holes in the universe. So in blue are these are the masses updated after the latest LIGO Virgo data release. So in blue are the neutron stars. I will not talk about them. In green here are the black holes that have been found with electromagnetic methods. So these are typically in the Milky Way or very nearby when the black hole is an X-ray binary, and the mass of the black hole is usually between 5 and 10 solar mass. Now the red points are the black holes that have been found by LIGO and Virgo when they are merging. And so this happens in distant galaxies up to redshift 1. And very simply, if you look at the green and the red, the masses are different. And the very simple question is, why are these masses different? And so the second question here is really, where do these black hole mergers come from? And so we've already talked about the fact that if you want a massive black hole, you need a low metallicity star. And so we find low metallicity stars in the universe, but it's quite a specific piece of star formation. And so this is something to keep in mind. It is very likely that massive black hole mergers come from a tiny piece of star formation. Now, this is all assuming that binary black hole mergers come from binary stars. There is a completely different hypothesis, which is equally valid, is that black hole mergers could come from dynamically rich environments like star clusters. So in these places, you would have stars evolving into black holes, sinking towards the center of the cluster where you have many n-body interactions, and that would lead to many mergers. Now, I'm not an expert on the evolution of clusters, so I will not talk about it too much in this talk. But what is important here is that stars that live in clusters are, again, a very specific piece of star formation. Most of the stars in the universe do not live in clusters. And so in both cases, black holes actually are very specific pieces of star formation. And that's what I want to talk about today. So I'm going to focus on binaries and looking for low metallicity stars. Basically, where do low metallicity stars live? So let's say we look at a random piece of the sky. You see blue galaxies where the stars are actually young. You see red galaxies where the stars are old. And you see galaxies that are too small that you don't even see them, which we call dwarfs. And very naively, I'm just wondering which of these places are good places to make binary black holes. Well, you have to know that different galaxies have different metallicities. If you look at the Milky Way, so the Milky Way is a massive galaxy, then on average, the stars in the Milky Way have a metallicity that is close to the metallicity of the sun. But that is on average. If you actually look into more detail, so this is data from a survey, you see that in the center of the galaxy, the metallicity can be about 10 times higher than on the outside of the galaxy. And you have the same if you go off the plane of the galaxy, your metallicity decreases with respect to the disk. And so even if the average is about solar metallicity, there's actually a strong gradient that you have to account for. Now, if we look at smaller galaxies like the Magellanic Clouds, the metallicity is between 1/4 and half of the solar metallicity. If we go 100 times smaller, the metallicity is about 10% of the sun. And then we even find really, really small galaxies where the metallicity is less than 1% of the sun. And so we have all this diversity of galaxies, all this diversity of metallicity. And so it is really important that if we want to study gravitational wave progenitors, we actually model this correctly. I strongly believe that if we want good gravitational wave progenitor models, we need to account for the complexity of star formation. So what I've been doing is essentially combining models for galaxies with binary models to make gravitational waves. So my binary model is based on a binary population synthesis code. So very briefly, binary population synthesis code take this complex evolution. They sweep it a little bit under the rug. Oops, what is? And what happens is essentially you give them an input. As an input, you give them the properties of young stars, basically the masses and the periods. And then they will use simplified models to evolve the stars and to make binary interactions. And the output will be a table of compact binaries or any type of binaries you actually want. And these methods are fast, so you can run millions of them very easily. And so you can sample different uncertainties very easily. So one of the outputs, for example, here is the delay time between the time you form your stars and the time where you form your binary black holes actually merge. And so you see here that in the dotted line, so this is one for stars that have a very low metallicity, you make many massive black hole mergers. But for the higher metallicity stars, the mergers happen only at much later times. So this is one of the outputs from the binary population model. Now I'm going to combine this with the model for star formation, and I care about low metallicity star formation. So I designed a semi-analytic model. So here in color, you can see the star formation as a function of the mass of the host galaxy. And then on one side, you have the metallicity, and on the other side, it's the look back to formation time. And so you see that most of the stars were actually formed in galaxies that are like the Milky Way, the massive galaxies. The stars were formed around redshift 1 or 2. And the metallicity is at least metallicity of the sun, or actually even higher. So it would actually be above the plot, but I'm not showing high metallicity because I only care about black holes. You see that maybe there is a little bit of star formation in small galaxies recently, but really there is not much. So this is star formation in the universe. Now I'm going to combine this with the delay time for binary black hole mergers and find out which of these stars will be progenitors for binary black hole mergers. So I'm going to show the exact same plot, but only showing stars that can make binary black holes. And so this is what we find. So we find that galaxies like the Milky Way can make stars that are binary black hole progenitors, but then we would only be focusing at the low metallicity stars in the Milky Way, but they exist. And then, for example, dwarf galaxies are also good places to make binary black hole mergers. The star formation is low, but the metallicity is also low, so these are also good places to make binary black hole mergers. And so this is exactly what you see here in an easier way. This is the merger rate of massive black holes as a function of the host galaxy mass. So obviously you see an importance of the Milky Way because massive galaxies, many stars, many black holes. But you also see a lot from dwarf galaxies. They don't make many stars, but many of these stars will make black holes. And what is interesting is that dwarf galaxies, especially at high redshift, are invisible to us. They are too faint. Even with the best telescopes, it will be very hard for us to have good information on these galaxies. And in some sense, we can use gravitational wave detections to understand these galaxies a bit better. So I'm going to skip this. So we found out that binary black holes can come from massive galaxies or from dwarf galaxies. Now we're going to talk a little bit more about compact binaries in a galaxy like the Milky Way. And so we're going to talk actually about sources that we can see with LIGO and Virgo, but also a bit about sources we will be seeing with LISA. So if you take the LIGO-Virgo merger rate, so this is what has been measured, we obviously, and you extrapolate it to the size of the Milky Way, we expect that many mergers have happened in the Milky Way. But it also means that we expect maybe 10 mergers per million year in the Milky Way. So we are not going to see a binary black hole merger in the Milky Way with LIGO and Virgo, unless we get extremely lucky, but it's extremely unlikely. But we can ask ourselves the question, how many binaries in the Milky Way have already merged? And how many are close to merger? And by close, I mean detectable with LISA. So LISA detects binaries before they merge with periods of typically half an hour, for example. So, okay, I need a model of the Milky Way. So this is our Milky Way, or this is our Milky Way. So usually when I give this talk in a real room, I can ask the people, okay, which one is the simulation? Which one is the observation? Here it's a bit less interactive. But if you've paid attention to the Gaia data releases, you will recognize that the lower panel is the real Milky Way, where you recognize, for example, the Magellanic Clouds. And the top panel is a simulation. So it's a simulation from the FIRE collaboration where I used to work. And so they aim at basically doing very high resolution simulations of galaxies, and part of the work is to try to understand the Milky Way. So I'm using this simulation as a model of the Milky Way. So looking a little bit into more detail, our Milky Way has many components. So you see this thin disk where most of the young stars live. Then you have what we call a thick disk where you have much older stars. So they're typically less bright. And then at the center, there is a bulge. And you see all around the galaxy, is what we call the stellar halo, where you have streams and satellites, for example. And all these components will be important to explain the gravitational wave emission we expect from galaxies like the Milky Way. And so I've built a model to look at gravitational waves in galaxies like this. So I take the simulation because the simulation gives me star formation, metallicity, position, any movements, any trajectories and things like that. I combine it with my binary model. It's the same model than before. And then I can fast forward it through gravitational wave emission. That's with simple equations. And then basically I have a list of compact binaries at different positions in the Milky Way. And so again, I want to emphasize the importance of a good model for star formation. So this is the model of star formation that comes out of the simulation. You see that basically in this simulation, most of the stars were formed around redshift 1 with a metallicity of about solar, but that there is a wide difference. So this is just star formation. And again, I'm going to now show you the stars that will make binary black holes. This is what we find. So we see that the high metallicity stars do not contribute to making binary black holes. And also the stars that were formed recently also don't make merging binary black holes because the evolution takes too long. But on the other hand, you see that there is a strong contribution from older star formation. And what is interesting is that I'm showing here with an arrow how the detection horizon of the detectors will improve. And so as the detectors get better, we will start to probe more and more this, this region of old star formation. Now, why is this important? So I have this model of star formation. Most models of binaries in galaxies like the Milky Way, especially for LISA, assume the model here in black. They basically assume that stars in the Milky Way have formed at solar metallicity at a constant rate over the past 10 billion years, maybe with a bit of a starburst in the bulge at lower metallicity. And so you see here that the color and the black are very different. And so this is going to be very important when actually making predictions of gravitational wave populations. So what do I find with this? I find that there are about 1 million binary black holes in the Milky Way, with a mean total mass of about 28 solar mass. I find that 10% of these systems have a total mass higher than 50, which is what LIGO and Virgo typically detects. And the mass spectrum I have is different from what is detected by LIGO and Virgo, but globally consistent. Now, why did I want to show this Milky Way model? So this is the model of the stars in the galaxy model. So I'm basically looking here at a very large scale. So you see the galactic disk a little bit on the right, and here we're looking really at the halo and the streams of the star that show where all the stars are. So this is for stars. I'm going to show you the same image for binary black holes. So the dynamic range is going to be the same, but the normalization of the plot will obviously be different. But just look at the colors. So on the top, you see the stars. In the bottom, you see the black holes. And what you see is that it's like the game of the 7 differences. You see that the black holes are much more present in the center, in the bulge, because that's where you have a lot of old stars, and in the outside of the galaxy, in the stellar halo, in the streams, and in the satellite, because that's also where you find low metallicity and old objects. Now, so we have about 1 million black holes in the Milky Way. The question is simple. What if LISA can find a black hole binary in the Milky Way? Wouldn't it be fantastic if we could say, oh, over there is a binary black hole. Let's just see what we can find out. So this was a question we tried to address last year with Alberto Cezanne and Antoine Petitot. And so we looked at the detectability of these black holes with LISA. So here the blue is the basically the noise curve for LISA. So the higher above the curve, the easier to detect. The lines show you where the white dwarfs live. So I will not talk about them yet. And the green shades show typically where binary black holes live in the LISA band. And so each red point here is one model for a galaxy. Oh, sorry, is one black hole in one specific model of the galaxy. So it looks like LISA will be able to find binary black holes in the Milky Way, but there is a problem. So when you have an optical telescope, you look at the sky, you find something, you know where it is because you have pointed your telescope. It's like your eyes, you know where you are looking. But with a gravitational wave telescope, most of the time you don't know where your signal comes from. It's like when you listen, you vaguely know it's maybe coming from here, but it's very hard to actually say, oh, it's there. And so LISA will not be able to know where the signal is. And it will not be able to know if it's a white dwarf binary very close by or a black hole binary much further away. It's like when you have the luminosity of a star, you don't know if it's a faint star nearby or a bright star farther away. And LISA is going to have similar problems. So we have to be able to identify the binary black hole somehow. And so what we found is that for some of the binaries, we will actually be able to measure the mass. And then if we know it has 20 solar mass, we know it has to be a black hole binary. So these are the ones that are shown in red here. So there will be a handful of systems where we know, oh, we have high signal to noise, we have a mass, and we have a sky localization of a few degrees. There is a binary black hole there. And with that, we can actually use the fantastic electromagnetic telescopes we will have. And let's say, for example, SKA, Athena, and try to find any electromagnetic counterpart. We can also know, oh, is this in a cluster? Are we in the halo? Are we in the disk? What type of environment is this? At lower frequency, it's going to be much harder because we won't be able to measure the mass, but we should be able to know if it's a white dwarf or not, because if it's a white dwarf, it has to be very close. And by then we will know the white dwarfs basically in the nearby galaxy. So LISA will be able to find and identify a few binary black holes in the Milky Way. But we should also talk about white dwarfs. So we've talked a lot about black holes because they come from massive binaries. There is a lot of interesting physics. Neutron stars in some sense have quite similar properties than the black holes. We expect a few tens, maybe a few hundred neutron star binaries with LISA in the Milky Way. But then remember, 95% of the stars actually will make white dwarfs. So we should not forget white dwarfs. They are the progenitors of type 1a supernova, for example. The advantage they have is that they have typically, they have some electromagnetic counterparts, even though they are faint. And so LISA is going to detect about 10,000 white dwarf binaries in the Milky Way. So we will have some sort of a map of the Milky Way. And that is very interesting. So I'm going to talk a bit now about white dwarfs and also even actual stellar binaries that will be detected by LISA. So LISA is a space-based gravitational wave detector. It's the L3 mission that was selected by ESA. It's going to fly in the mid-2030s, and it will be detecting millihertz gravitational waves, so completely different range of frequencies that we have now. So it's like the same thing as having the first X-ray telescope. We're going to have a lot of discoveries. So we've all seen these images of the galaxy in many different wavelengths, showing very different things. In 2035, we will have an image of the Milky Way in gravitational waves. And I think this is a very nice and powerful idea. So again, if we want to prepare for LISA, we need to have this model of the Milky Way. So that's what I've been doing the last few years. So we're talking here about white dwarfs. So white dwarfs are a bit different than black holes. And you have to know that there are essentially two types of white dwarfs. So on the right here, I'm showing white dwarfs that come from stars. Let's say 2 solar mass stars. They burn their hydrogen, so then you have a helium core. They start burning helium, then they have a carbon oxygen core, and then they become white dwarfs. And in this binary, there have been a little bit of mass transfer, but nothing very violent. And so you end up with 2 carbon oxygen white dwarfs. They have a mass of about half solar mass each. And the frequencies the periods they have can be between 1 hour and millions of years, actually, if the binary never interacted. Most of the white dwarfs are carbon oxygen white dwarfs. Now, if you have stars that form really close to each other, there is going to be a phase of common envelope interaction, very soon after the stars are born. And that means that the envelopes of the stars are gone, and the stars will never be able to start burning helium. They will stop after they are done burning hydrogen. And so the cores of these stars are helium cores. And these binaries are very close to each other because of the common envelope. And these white dwarfs are really small. And so we call these helium-helium white dwarfs. And so there's not many of them in the Milky Way, but they all have periods of maximum a few hours. And so they are very good LISA sources because they have these very short periods. What you have to understand is that to make a helium-helium white dwarfs takes a long time, between 2 and 13 billion years. To make a carbon-oxygen binary is much shorter. It's always below a few billion years. So the timescales to make these binaries is different. You also have to know that all the binaries we will see with LISA will actually merge pretty soon. So it means that the white dwarfs have to have formed recently. Otherwise, they would already have gone. Okay, so we have two types of white dwarfs. We have a model of the Milky Way. If you combine these, this is a map of the helium white dwarfs in the LISA band in the Milky Way. And you see that you have a lot of binaries in the bulge, in the circle in the middle, and in the halo. So this is almost spherically symmetrical. This is because we're looking at old stars. Now, if we look at the carbon-oxygen white dwarfs, they live much more in the disk because they are much younger. And so it is very important to understand, to have this good model so that we can actually understand where these different populations live. We also found that LISA is going to be able to detect white dwarfs even in the satellites of the Milky Way, which I think is pretty exciting. And so this is the model. Let's think a little bit about what LISA will detect and what it means for the multi-messenger astronomy, because white dwarfs are observable with electromagnetic telescopes. So I found that about 10,000 systems will be observable by LISA, will be observed by LISA. So what that means is that LISA will say, oh, there is a binary somewhere with this frequency and this gravitational wave amplitude. That is the information that LISA gives us. It does not tell you the masses of the object. It does not tell you where it is, unless you have very good signal to noise. So that's too bad. The good thing is that the gravitational wave flux decreases as 1 over the distance, while the electromagnetic flux decreases as 1 over the distance squared. So gravitational waves have the potential to look much further. They don't suffer from dust extinction. They don't suffer from spatial crowding. So the observational biases you have are very different from the electromagnetic observations. And so this is, here I'm showing the LISA detections of white dwarfs. Basically, the thin line shows the global population in the Milky Way model I have. And the colors show the binaries that are individually resolved and observable by LISA. And you see that basically anything on the right side of this line is resolved. So basically LISA will be complete for anything that has a period smaller than 11 minutes. If there is a binary, it has a period smaller than 11 minutes, and it is somewhere in the Milky Way, LISA will find it. In that sense, it's a complete survey. And that is something very interesting when we want to do statistics for a stellar evolution, for example. What does this mean for electromagnetic observations? By the time LISA comes, LSST will have given a lot of data. We see, for example, here, because the spatial distributions of the two types of white dwarfs are very different, obviously, they will be found in different places by LSST. And so we need to adopt search strategies to find them in different locations. And so the two plots I'm showing here are my model. And then the bottom left plot is the old model that has been used in the LISA collaboration for a long time with a much simpler model of the galaxy. And you see that these models are very different. And so if we want to prepare ourselves both for the data analysis for LISA and for electromagnetic detections, we need to start using these better models. Now, I've talked about compact objects, but LISA, something we found last summer, we found that LISA is also going to be able to detect a few living stars. And by living, I mean stars that are still burning hydrogen or helium in their core. And so these are binaries where you have one compact object, so a white dwarf or a neutron star mostly. And then the other star the envelope has been removed by the common envelope mechanism, but you still have the core of that massive star and it's still producing energy. So these will be sources that typically have periods of 3 to 6 hours. And a few of them will be detected by LISA, as you can see here in the dark blue. And there won't be many of them, somewhere between 5 and 10 we predict. But the advantage is that they are multi-messenger sources and we will probably be able to find them with electromagnetic telescopes. And that is very interesting. So I've talked a lot about what we can do with models. I want you to dream a little bit and think about the future. So I've talked about what we can do with the recent LIGO and Virgo observations. So the collaboration has finished the third observing run and has released the data for half of it. In that data, there are 37 binary black hole mergers. And so with 37, you can start to do some statistics. And if you look at the archive, there's already a lot of work, people trying to analyze what these binary mean, especially in terms of the origin of mergers. Remember the question of binaries, clusters, and what it means for binary evolution. But then again, I want to emphasize that if you want to do it right, we need good models for star formation. So the project I've been working on for the last years is to use this Milky Way simulation, combine it with binaries and predict mergers in binaries. So I've presented this here. In the meantime, for the past 2 years, I've been working with experts of globular clusters to basically map star clusters onto this galaxy using the properties of the star-forming gas. Then map black holes onto these clusters and determine black hole mergers from clusters in the same galaxy. So we've been working at this for about 2 years now. We hope to have we've had one short publication, but we hope to have most of the method papers out within the next few months. This will be the first time that there's actually a consistent comparison of the two main merger models based on the same model of star formation and the same model of stellar evolution as well. And I think that is going to be an important step forward for the field. And this is basically doing this, but at the scale of a larger scale volume, basically a cosmological volume is what I will be doing the next few years with my ANR project, essentially. So this is happening now. Let's think in 15 years, LISA will be flying. So in terms of white dwarfs, I've shown you that LISA will be complete for binaries that are up to 10 minutes in period. We'll have an idea of galactic structure. LISA will also find a few binary black holes and actually be able to locate them, and a few other types of binaries. There's a lot of potential for multi-messenger astronomy. I'm thinking more and more about the connection between what Gaia and all these spectroscopic surveys that are starting now, and then LSST will teach us before LISA flies and how we can connect these. And so this is really something that the collaboration is working on now, is how to prepare LISA in light of what we have now. The other important detector in the mid-2030s will be the Einstein telescope. So the Einstein telescope is the next generation ground-based detector. It's the new LIGO or the new Virgo. It's a 10-kilometer triangle underground. So this is a European project. It will be about 10 times more sensitive than LIGO and Virgo currently. So it's a completely different type of observatory. It's like going from a 30-centimeter telescope to a 4-meter class telescope. The science will be completely different. And so it will be able to detect about 1 million binary black holes per year. So you can imagine that the mass spectrum we will have there will allow us to do a lot of stellar physics, but also because we will be able to see up to redshift 10, have black holes coming from the first stars, disentangle the different formation channels and their redshift evolution. We will be able to detect binary neutron stars up to redshift 2. So we will catch the peak of star formation and look at and have different formation channels. For exceptionally good events, we should be able to, for example, measure the equation of state for neutron stars extremely well. We expect the detection of intermediate mass black holes if they exist. And there is also an expectation for Einstein telescope to detect a cosmological background of gravitational waves, which is the equivalent of the CMB, but with gravitational waves. And so the Einstein telescope is still is a project that has just been submitted to the European for European funding. It's still being designed and the collaboration is still being set up. There will be an Einstein Telescope France meeting early February. If you're interested, you can sign up. It's free, it's remote. If you want to know a little bit more about the science, we will be able to do. And I'm going to stop here. Thank you very much.
Thank you, Astrid. Thank you very much. So we have now time for questions. So please raise your hand if you want to ask a question to Astrid. Okay, maybe I will start to help the process to. So in fact, I had a question about all your work about the population that can be probed with LISA. When you try to model the detection by LISA, do you? I know nothing about the signal analysis of LISA, but is it just a question of intensity of the gravitational signal, or do you have also to take into account the fact that LISA will see so many sources together that you have additional conditions?
So the detection with LISA is very different from the detection with LIGO and Virgo. So LIGO and Virgo, you have noise all the time, and sometimes you have a little bit of something, and that's your signal. With LISA, you have many signals superposed all the time, because these 10,000 white dwarfs that we predict, they're emitting continuously all the time. So you have them in your signal all the time. You also have essentially a foreground of the unresolved white dwarfs that you cannot resolve, but that are making a little bit of noise and that are always in your data. So LISA, you have 10,000 signals all the time. So it's much more complicated. So for very loud signals, for example, you have a supermassive black hole merger, they will be much louder than anything else. So those we should be able to isolate easily. And also the frequency evolution is different, so they should be able to find easily. Now for galactic binaries, let's say we want to find the binary black hole within the sea of white dwarf binaries, that is going to take time. So the global idea is to have some sort of a global fit where you try to fit every single source at the same time and then remove resolved sources as we know, once we know them, remove them from the signal, and then you see what is left and you can start analyzing that, and you remove more and you do that. And that will go better over time, obviously. But it will take some time, and the data analysis for LISA is complex, absolutely.
And at the end of this analysis, what kind of localization can you expect?
So for galactic sources, it depends on the signal to noise, which depends on the mass and the frequency, and obviously the distance. For the binary black hole, we expect 1 or 2 with a localization of a degree or 2. All the other ones will be much bigger. White dwarfs, I forgot the exact numbers. I have to look it up. There will be a small fraction that will be easy to localize, but many of them will be much more washed out. So it will probably what I would expect is that if we want to associate them with an electromagnetic counterpart, we will need catalogs from Gaia, LSST, whatever, and there will be some kind of matching, but it will be non-trivial for many of them. Yeah.
Thank you. Questions? Please raise your hand.
I have one, Frédéric.
Yes, please.
I cannot raise my hand. That's why, because I'm the
Okay.
I'm the organizer. That's why. So that's a question about the stellar evolution that leads to stellar black hole binaries. So there are several uncertainties, if I understand correctly, especially whether the stars are able to share their envelope, if they have rotation, etc., are very important for those stars to synthesize their metals and be able to produce a Wolf rate wind. Also, there are some important uncertainties on whether the most massive stars are able to trigger or not the core collapse supernovae. So to what extent, what are the levels of those uncertainties and the consequences on the detectabilities?
So you made a very honest summary. The uncertainties are big. Now, I think 5 years ago, before the gravitational wave detection, I would have said that, for example, the parameter that governs the common envelope is unknown by orders of magnitude. But now we have had the first detections, so we do have an idea of the merger rate. We do have an idea of the mass spectrum. So there is already a region of parameter space that is completely ruled out. So we're not completely blind anymore. I think probably most of these things would be able to vary within one order of magnitude is probably more realistic. Although, for example, things like the ability to trigger a supernova at very high masses, that is going to remain uncertain for a long time because we need a lot of data at high mass. So you can look at this in two directions. You can consider the fact that these uncertainties are a problem. Or you can say, okay, I'm going to use my gravitational wave detections and try to infer these parameters. And that's what I hope to do in the next few years, is to say, okay, so the next detection run will be 04. So that is going to start in the middle of 2022. And we expect over 1 year that there will be between 300 and 400 detections. So that is good enough to already start doing some decent statistics. And with that, we should be able to say, okay, stellar winds is probably more like this. Supernova kick, we can rule out strong kicks up to, I don't know, 100 kilometers per second. I just said that, don't quote me on this value, and I think within the next few years, we'll make a lot of progress. And with Einstein telescope, we will completely solve this, I think. So it's not that bad anymore.
You at the beginning of your seminar, you have shown the distribution of delays for binary black hole mergers. And you know that for neutron stars, there are a lot of debates about the possibility to have a population of short delay, because it could have an impact on an early enrichment in air process elements. And do you find such a population for black holes? And are there parameters in the stellar evolution that favor or not such delays?
My first answer is I don't know. I don't think enough about neutron stars. So how does this channel happen again? Can you?
Well, the idea is that if you want to, you know that air process elements like europium are observed in some low metallicity stars.
Yes.
And so if you want to produce this europium in the very early universe with mergers, you need to have a population of binary neutron stars with short delays.
Yes.
So I wonder whether for black holes you obtain here, it seems that the cutoff is at 10
million, yeah.
It's already quite short, yeah.
Yeah, you could. So in this this plot, I'm only showing progenitors of massive black holes.
Yeah,
The ones that have at least
Yeah.
25 solar mass, so it's not the global population.
Yeah.
I think, so I'm not an expert on neutron stars again, but you can probably, there are enough parameters that you can probably allow for short merge, for fast merger channels. I think it is possible. I think to do that, you need the common envelope to happen at the very early phases, bring the stars very close to each other so that the merger happens very quickly, I think.
But what
And
is
there must be cases.
In your plot, it seems that such short delays are favored at low metallicity, which is interesting in this context because you need that mainly in the early universe. So.
True, but then if you have low metallicity, you have low winds, so you keep a lot of your mass.
Yeah, so maybe you form less neutron stars.
But you will form some, I guess. The stars that are right in the good region of the initial mass function will make neutron stars. Maybe. I honestly don't know enough.
I have many other questions, but don't hesitate to raise your hand.
Friedrich, I have one. Maybe.
Yes, please.
Also can. Hi.
Hi.
So I have a couple of questions, very, very naive. So the first one is like the fact that with your analysis, you can predict like how likely LISA would be able to detect like a binary black hole merger in the Milky Way is more. I mean, the fact that this is in the Milky Way is more a curiosity, or there is it's really different the science that you can do if the binary is in the Milky Way with respect to a satellite galaxy or.
So LISA will, so we're not going to detect the mergers, but just the black holes as they turn around each other.
I said the spiral. So
yeah.
Yes.
So when I say Milky Way, I usually think the Milky Way and the nearby environment. It could be a satellite, but statistically, it's going to be actually, for LISA to be able to detect it and to localize it, it's going to be pretty nearby. So the reason I find this interesting is I see two reasons. One is that if we know where it is, we know the environment where it formed. Let's say if it's in the bulge, it probably has different conditions from the disk, or maybe it's in a star cluster. And it would be the only binary black hole, presumably, for which we have a clear indication of where it formed. And I think it will be a very clean way of thinking about formation channels and environment. And the other thing is, if it's nearby, I really hope, I expect that there would be very deep searches for electromagnetic counterparts. Maybe there won't be any, but maybe there is a little bit of accretion or something. I don't know, but I imagine that there are some people working on emission models for even isolated black holes. If we know where it is, people are going to search, and if there's something, it would be incredible. These are the two reasons why I would be very excited about this.
Thank you. So the other things, like at the beginning you mentioned, yeah, obviously, yeah, the things you just also discussed with Friedrich about the mass and how the metallicity influenced the mass of the black hole. But you always consider black holes that have a star formation origin. I mean, because now in cosmology is very fashionable to talk about primordial black holes. You never consider that option in your.
I don't have anything against
I
it.
asked because now I don't remember exactly, but you did really well the all the timeline in like from when the from when the binary forms until when we detect all the the different time scales. So yeah, I was just wondering if any change if these are primordial black holes with respect to.
So I don't know much. Yeah. So I don't know much about primordial black holes and the times. You would find them in the very early universe.
Yeah.
possibly before the first stars. So if we see mergers at very high redshift, let's say with Einstein telescope, depending on the masses we find, that may be an indication of something primordial. Although I'm sure there will be a stellar astrophysicist who will invent a way to make it work with stars.
Yeah, that's a point.
For me, I think the convincing evidence would be if you look at the plot I'm showing here, so in green is the detection limit for Einstein telescope as a function of mass and redshift. And you see here at very low masses, it will be able to make some detection. So these are objects that have a mass below 1 solar mass. And so if Einstein telescope detects the merger of 2 objects below the mass of the sun, with stellar physics, I have no idea how to make this. And so I think if you find something there, then it's a pretty good signal that it's primordial or something very different from stellar origin. So I would put my bet there, but that's me.
So it's more, yeah. So it's more looking for small mass that would it would be harder to predict that with an astrophysical mechanism, which is compared to higher redshift. Okay.
Yes, I think there's no way you can make one with a star, as far as I know. But anything else, I think you can always find. I could imagine that people can always find a way.
Okay. Thank you.
Thank you. I think that Irina has also a question. Please, Irina.
Astrid, thanks to the wonderful talk. I was wondering, what's your take on let's go to the massive end of the black holes. What's your take on the detection in the parent stability supernova gap? And do you think it's like a smoking gun for the cluster scenario, or there is still some room for the stellar evolution? There were the papers on the uncertainty in the nuclear reaction rate, etc., that could allow for that.
So the question is about the parent stability supernova gap. So there's basically stellar physics predict that beyond a certain mass of the core of a star, there is no supernova explosion. Basically the supernova explosion doesn't leave anything behind, and you don't have a black hole. And so with this, we don't really expect black holes between 60 and 140 or 150 solar mass. I don't remember the upper limit, with simple binary evolution. And so, for example, the detection at LIGO and Virgo announced 1905-21 sits right in that gap. And so the question is, if we find many more of these, does that mean these binaries come from another channel, for example, cluster dynamics, or can we try to make a few changes to stellar astrophysics? I'm not sure myself. I think if we find many, and depending on the information we have on the spins, because the spins also give us an indication about formation channel, I would be more comfortable with the cluster channel, I think. Also, it will depend on what we find at lower masses, because obviously it's a continuum. Now, I think given how much uncertainty there is in massive binary physics in general, I wouldn't be surprised if the lower and the upper limit of this mass gap can move a little bit, just because most things are still uncertain. But that being said, I think at some point, the fact that you're going to have pair creation, you can't really escape it, I think, from basic physics. So I think you could move the limits a little bit. Because the paper you mentioned with the reaction rates, their mass limits changed with what, 5 solar mass, 10 solar mass? Do you remember?
No, I think they claim that it's up to 20 solar masses, if I remember correctly. I know I'm not at all an expert there.
I had something smaller in mind, but maybe you are right. I think we will be able to move it a little bit, but not completely. If we find many black holes in that region, I think clusters will be the answer, I think.
I mean, it also depends on the uncertainty of the measurement. So with the uncertainty in the measurement, all that.
Yes, exactly. So,
but the question is whether you will see a clear signal in the mass distribution.
I'm not sure, because then also depending on the metallicity, you have different black hole masses. I don't know how sharp a cutoff will have. For me, it's hard to predict. I don't know.
Yeah, no, it's more work to do.
Yes, more work.
Okay, thanks.
So I think that maybe we should thank Astrid and stop the question session, but maybe we can, if a few want still to